All right.
So we left off on Friday looking at two more of our vocab terms, the periods and the groups. Which ones are the ones that go up and down? Periods or groups? Groups go up. You see the word up in the word group, right? And then the side to side, those are the periods, all right? So you are going to have to be able to identify. So if I say, this is the element that is in group 1, period 5, you should be able to find it kind of like playing Battleship and be like, oh, cool, cesium, right? Which I just made up. I don't know if that's really where that is or not. We're going to actually play bingo one day this week, and so you are definitely going to have to be able to keep those groups and the period straight as well. Couple little things to recap, some important things. How do you know which one of the numbers, the atomic number or the mass number, is going to always be the small one? Is that going to be the atomic number or the mass number?
Atomic number.
Atomic number. Remember, it's teensy tiny like the atom, atomic atom. And then obviously then the mass number is the massive one because it includes 2 subatomic particles. Which 2 things are you adding up to get the mass number? Who remembers that? These are the 2 things that are also in the nucleus, if that helps. Very nice, the protons and the neutrons. And then what is associated with the atomic number? Which one of our subatomic particles goes with the atomic number?
Protons.
Good, and these are also the ones that are permanent, right? They're the fingerprint. If you change the number of protons or you change the atomic number, you're actually changing elements. So if you have carbon and you add another proton, you no longer have carbon. You would have nitrogen. Yes, nitrogen. How do we figure out the number of neutrons? Because this is the only one that doesn't have a specific number that's already on the periodic table. We have to do something a little extra, and I see some eyeballs like going looking over at the board, which is awesome. How do we do that? How do we find that? It's one extra step. It's not just like reading the number on the chart, because it's not on the chart. What do we do? Michaela, you're looking right at it. What do we do?
Mass number minus the atomic number.
Good. And so if you look up here in the corner, when we have things that are important or helpful or like a formula or an equation, I'm going to try to keep a running list over here for the unit, and that way they'll be up there all the time, even during your test and things. So I know it's a little sloppy where I wrote it here on Friday, but up there in the corner, it's going to kind of start a running list of important things. Also, I believe I forgot to tell you guys, and you'll learn, I'm not the best morning person, and unfortunately I do my notes, and record them. So even people at home, I didn't point this out. Sometimes I forget things, first of all, so sometimes I backtrack with you guys. On your periodic table, in the bottom corner, in my handwriting, I have that mass number minus atomic number equals the number of neutrons. And then in that parentheses, P plus N minus N, P plus N minus P leaves you with the N, meaning P for protons, N for neutrons, and using those abbreviations to kind of shorten things up. So, all right, so that gets us to slide number 41, which is where we're at today. And you guys already answered this. Hopefully my equipment is working better today than it did the end of last week. So the periods are horizontal, like you row a boat. And then the groups, they're going to be our vertical, our columns are up and down. So I'm a real visual person, and I know a lot of you in here are as well. So kind of visually getting to see it with color is helpful. All right, so the groups go up and down. We also said that the groups are organized by number of electrons in their outer energy level. So these all have 1, 2, 3, 4, 5, 6, 7, and the ones over here are 8. And that's a really important thing that we're going to get to later on, I think this week. Okay, and then the periods are going by protons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And so as you go across, you're just basically reading left to right and adding a proton as you go. So hydrogen, helium, lithium, beryllium, carbon, fluorine, right? Like the song, I'm not as good as them. I will show you a 6-year-old that can sing that whole song though. It's pretty amazing. I can sing it if it's on, but not alone. Okay, so this is just showing another way to look at the periodic table. It's helpful when it's color coded. We're gonna actually color code some of ours, not like this fancy, but hopefully we'll get to that today. So I wanna point something out right here. These blue ones right here, these are called the transition metals. They are not as easy to predict or determine like how they're gonna behave. So sometimes we're gonna skip those in, some of our activities. So if you look at these tall columns, these are all gonna behave in a certain way. And so those are gonna be more predictable. So those are gonna be the ones that we deal with the most. Okay, here is another vocab term, super important. This idea of valence electrons is what determines how these elements react, what they do with each other, how they behave. It basically dictates a lot, all right? So this is a vocab term. You say the word valence, okay, valence. These are the electrons in the outermost energy level. So if you remember back to that Niels Bohr model, where he had like these perfect little tracks or circles or layers, and that's where the electrons stayed. We know that that's not exactly true, but remember how I said it's really helpful in like practical ways, like for us to imagine them that way? So we are going to be looking at that model. So if we're thinking of the outer electrons, they're the ones at the farthest away from the nucleus, okay? So if I would put all of you guys in a big group, there's quite a few of us in here. If we got in a big group and I had a big fire hose and I start spraying, who's going to get hit first? The people on the outside of that circle or the people on the inside? What do you think? What do you think?
Outside.
Outside. Well, the electrons on the outside of the atom are going to be the ones that also have the most chance of getting affected by something or interacting with something. So the people on the outside of that big mob, they're going to be the ones that get affected by that water first. And so it's these outer electrons, which we call the valence electrons, that are going to be able to interact with other atoms. And those electrons, sometimes they might share them, they might give them away, or they might take them, right? So that's kind of the options that are available to those outer electrons. And it's because they're in that outermost area of the atom that it only makes sense that they're going to be the ones that are going to react. Just like you guys, I mean, it's common sense. Like if you're in a big group, the people on the outside are going to be the ones that are affected by something first. Same thing with the electrons. So again, common sense and logic. Try not to memorize it, just think about it logically. These electrons are farther away from interacting with anything outside of it because they're closer to the center. So it's these valence that are the ones that can do the exchanging and sharing, because they're the first part of the atom that would become in contact with another atom. Okay, so elements in the same group, vertical column, are going to have the same properties. And that video that we watched on Friday and the periodic table, like the chorus of the periodic table song, gets into that. So all of these have one valence electron. Now, from here on out, I'm going to be very, very precise and deliberate when I say valence electrons or whether I'm saying total electrons. Remember, the number of protons should equal the number of total electrons. That is not the same thing as valence electrons, because there might be one valence electron here, but this one might actually have like 5 electrons total. So when we're talking here on out, usually we're going to be talking about those valence electrons, and that's not the same as the total number. Okay. The only time that that's true is actually with hydrogen. The total number is the number of valence. All right, so one thing I want to point out, if you go here This says 2. The rest of them have 8. Helium is special. It is so small, and I'm gonna go back for a second. It's so small that it only has 1 energy level for the electrons. And that energy level is so small, it can only hold 2, so 2 makes it full. And then you go to the next level. That's really the only thing you need to know, is that this first energy level, it can only hold 2. And so when helium has 2, that makes it full, which is why it's all the way over here with all the other ones. The next outer energy levels, they can hold 8, all right? And so because that outer level of all the rest of them can hold 8, 8 makes it full and satisfied. So once you reach 8, you have to drop back down to the next energy level and start filling them up again. Right, so let me get back to the notes here. And like I said, this is all gonna come together. Sometimes it's kind of like, I get these blank looks like, what is she talking about? It'll come together, I promise you. So they're grouped this way, and the table starts back over on the left-hand side because these elements are all going to react the same. They're actually very, very, very reactive, right? And we'll get to that in a minute. But they all react the same because they have 1 outer energy level electron. These all have 2. These all have 3, 4, 5, 6, 7. These are 8, but helium is 2. Helium's special because it's full, even though it's only 2, because that's all it can hold. All right. Notice these are blank. The transition metals can vary. Sometimes they will take 3 electrons, sometimes they'll give 3, sometimes they'll take 4, sometimes they'll give 4. So we would have to have more information given to us to know how they're going to react. These ones here, the tall columns, we know 100% how they're going to react. We don't have to have any other information given to us, right? All right, so valence electrons can also be thought of as the number of electrons that an atom needs to gain or to lose to become stable and satisfied. And this is basically what's going to determine how they react. Are they going to give up 1? Are they going to take 2? What are they going to do, right? Because it's very set. There's no guesswork to it. And again, I keep saying more about that later, but it all has to kind of come together. It will, promise. All right, so besides just looking at the number of electrons, those vertical columns, and the number of protons, if you're looking at the horizontal rows, there's other information that the periodic table can show us. There's certain elements that share properties that allow us to even group them further. So here's a few more vocab words. Metals, like the alkali and alkaline. The nonmetals, and something called metalloids. Metalloids are a combination of properties that are similar to metals, but they also have some properties that are similar to nonmetals. So they're kind of unique. Then we have these halogens and noble gases, right? And so all of these should look familiar for your vocab terms. And so hopefully after we go through them today, it'll make a little bit more sense, put all this together. So obviously we know what metals are. They're shiny, they're malleable, meaning that they can bend. They're ductile, they conduct heat and electricity well, which is why we use them in our wiring. They usually are very dense and they have a high melting point. So it takes a lot of heat to melt them. Yes?
Is it steel a metalloid? Is it perfected iron, basically?
No, that'd be an alloy, where it's like a mixture of metals.
I thought metalloid was another word for alloy.
No, it sounds like it. It sounds like it, but no, an alloy is like a mixture of 2 different metals. Strictly metals. That's a good question though. That is, they do sound alike.
That's confusing.
It is a little bit, you're right. So, and I actually always think of the word alloy when I'm saying metalloids too. So if you see all these blue, these are the metals. Okay, those are the metals. Now, specifically, here's a couple more vocab words. The alkali metals. They are found in group 1. They are very reactive. Actually, they're the most reactive of all the metals. They don't even occur freely in nature because they react so quickly and so violently. As soon as they're there, bam, they're going to find something to react with. They only have one electron in their outer shell. Their main desire in their little atomic life is to get rid of that one electron. Because if they get rid of that one extra electron, they get to drop down an energy level, and basically it kicks them to having a full energy level, because you can't add an energy or add an electron until you filled a level. All right, so if we, and again, like I said, it'll start, let me go back real quick. It'll start making sense as we get more experience with it. Let me go back. So if this level is full, we have 8 in the outer level, it can't hold anymore. So because of that, it's going to drop down, and now you have to add 1. So all of these want to just get rid of that 1, and then they would be back to having a full energy level. The goal of the atom, why, I don't know, but the goal of the atom is to have that full outer energy level. All right? So the best way to do that is either to get rid of a few or to take a few. And these alkalis, they're going to get rid of 1. So if they lose that 1, then they can drop down and become full again. And that is their main purpose. Okay? So if they lose that 1, give it away, they're happy. And that's what they want. They want to be happy and satisfied. One thing I want to say, we've said neutral, like where you have the same number of protons and the same number of electrons. Neutral doesn't always mean satisfied and stable. They're neutral when they have that extra electron, but they're not stable. They're not satisfied. If they get rid of that, then they become stable. And so lithium, sodium, potassium, rubidium, cesium, and francium, all of those in group 1 are our alkali metals. Now hydrogen up here at the top, it is in that group because it has 1 valence electron, but it is not considered an alkali metal. So hydrogen and helium kind of get plunked up the top, even though they don't match the rest of the group perfectly, just because of how their electrons match up. All right, so the alkaline, this is group 2. They're still reactive, just not quite as much as the alkali. Usually they do not occur freely in nature again. They react so quickly. They have 2 outer electrons, or 2 valence. So they're going to lose those 2. They're going to lose those 2. And when they do that, they drop down, and now that energy level's full. So it's not that you're changing beryllium, magnesium, calcium. You're not changing those elements into another element. It's still staying the same element because you're keeping the same number of protons. But what's happening is that number of electrons has changed, and so now it is satisfied and stable if it loses those 2. And we see those right here. All right, the nonmetals. These are typically going to be solid. They're dull and brittle. They do not conduct heat or electricity. Typically, they're going to be the ones that gain electrons. They're going to be taking those electrons from the metals. They're not very dense, and usually they have a low melting point. So, for example, if you look over here, our nonmetals are in the purple. You can kind of see this transition, this stair step. It's not like a perfect break, like it kind of, the metals here and our nonmetals in the purple. So there's not a whole lot of the nonmetals, but those are going to be the ones that take. And then we get to the metalloids. they're really unique because they have certain characteristics that are both metals and non-metals. And so they can do some really important things. Because they are only partial conductors, they're good in our computers and in our a lot of our technology. The silicon, the arsenic, obviously arsenic not in our technologies, but in our microchips and things like that, you'll find a lot of these, they can still be dangerous, obviously, but they serve a lot of unique purposes that a metal can't do and that a non-metal can't do, but because they have characteristics of both, they can. And they're right here, which makes sense that they're gonna be the ones that separate the the metals from our non-metals. So they're kind of right there in the middle, along that stair step. I'm not gonna make you have to memorize what are the non-metals, what are the metals, what are the metalloids, right? You have the periodic table to look at for that, so you're not gonna have to memorize anything like that. And then finally the halogens. These are found in group 17 of the periodic table, or valence group 7, and I'll explain that here in a minute too, the difference of that. They are reactive non-metals. They have highly variable physical properties, meaning that there's a lot of differences between the halogens. So at a solid, iodine, so you have solid iodine, liquid bromine, gas for fluorine and chlorine, all at room temperature. So that's not like they're all solids or they're all liquids or they're all gases. They're different even at room temperature. Some are naturally solids, some are naturally gases, some are naturally liquids. So that's kind of unusual. They have 7 valence electrons. 7. Our goal is to get 8. So all the halogens want to take an electron from something. Probably going to be a metal, right? So if you have 7 and you're 1 away from getting to 8, it's easier for them to add an electron than it is for them to give all 7 of them away. Okay. They're ready to take 1 electron. Typically it's going to be from an alkali or an alkaline metal. And our next unit is going to be all about bonding. So we'll talk about ionic bonding, where you give or take electrons. So the alkalis are going to be the givers, the non-metals are going to be the takers, and they're going to form an ionic bond. There's also a situation where they could share electrons in a covalent bond, but this unit we're mostly going to be talking about ionic bonds. The metals giving, the non-metals are going to be the takers. And so fluorine, chlorine, bromine, iodine, and astatine. Those are going to be our halogens, and they are right here in group 17. Because if you look up here at the top, you have 1 through 18, if you include these 10 groups in our transition metals. If you don't include those, you have 1, 2, 3, 4, 5, 6, 7, 8. So sometimes you will see valence group. This is valence group 8, but this is also group 18. Right? And we'll get into that a little bit more later, but you'll see it both ways and it can get confusing sometimes. 1 through 18 if you're including the transition metals. If you're only counting the tall columns and ignoring these 10, these are basically 13 minus 10. So this is group 3, group 4, group 5, group 6, group 7, and then group 8. Right. All right, noble gases. These are group 18. They are not reactive at all. They have 8 electrons in their valence. 8's what they want to be. So they don't do anything. They're called the inert gases, inert meaning resisting that change. They're just going to sit there. Under normal conditions, they're odorless, colorless, And those are our neon, helium, argon, krypton, xenon, and radon. They don't want to react with anything. They're perfectly happy exactly the way they are. Okay? And so they're over here. So these groups, the alkali, the alkaline, our halogens, our noble gases, those are major groups. They share major characteristics. They also are very predictive, like we can predict exactly how they're going to react. Give up 1 electron, give up 2 electron. These are going to always take 1 electron. These are always going to take no electrons. They're not going to do anything at all. So we can be very, very confident in how these certain elements are going to behave. Okay. All right, let's go back. Let's take a look at, let's look at the elemental phoniness.